So we will find out the shear stresses at a section of beam. Suppose we have a simply supported beam carrying uniformly distributed load. The beam has a thickness, as we will discuss the shear stress, so its thickness should be taken. Now we have two sections. One is AB, second one is CD. Okay. Now, due to this section is basically a simply supported beam carrying a uniformly distributed load. For uniformly distributed load, the shear force and bending moment will vary along the length of the beam. Consider two sections AB and CD of this beam at a distance, let dx distance apart. Okay. Now, we will draw this section in a little magnified way. This section is extended in both of the sides. Here we magnify AB and CD section, where from the middle, from the centroidal axis, that will be the neutral axis. Now, we take a section at a distance of y1 from a neutral axis. We are taking a section at a distance y1 from the neutral axis. Now, for that particular layer, the layer above y1 distance from the neutral axis. So, from this particular layer, let in the direction AB, the stress is sigma, and here the stress is sigma plus d sigma. As uniformly distributed load, the stress will vary section to section, and the bending moment will also vary from section to section. So here bending moment is, say, m. Let here the bending moment is m plus dm. Okay, this is the scenario. Now, if we look at the cross section, so this is the basically neutral axis plane. Here this distance is y1, and we just name them as say this plane E, F, G, H on the cross section. So we will take this cross section EF, GH, okay, and let its width is B. Now, if we take a cylindrical object, then at this point the stress will be sigma, and if the cylindrical area is dA, we will discuss later. Slowly we will advance. Now let us have these two planes AB and CD, two cross sections having dx, having at a distance of dx, and of course, as we said, this is the simply supported beam but carrying uniformly distributed load. Shear force and bending moment will vary section to section. So at AB, if bending moment is m and stress is sigma, in CD the stress will be sigma plus d sigma and bending moment m plus dm. Okay, let at the section AB, write it up, let at the section AB, F is the shear force, M is bending moment. Now at section CD, shear force value, let F plus dF, bending moment m plus dm, and I is moment of inertia of the section about neutral axis. Okay, now let it is required to find out the shear stress on the section AB at a distance y1 from the neutral axis. So basically we have to find out the shear stress on the section EFGH. Now this image here on the right hand side, okay, on the right hand side this image shows the cross section of the beam. On the cross section of the beam, let EF, this line, EF line, be a line at a distance y1 from the neutral axis. Now consider the part of the beam above the level EF, this hatched section, and between the section AB and CD. Okay, so this surface is AB and the surface behind it is CD, the end is CD. Okay, now this length will be then dx. Now this part of the beam may be taken to consist of an infinite number of elemental cylinders, each of area dA. So as I was saying, the elemental area of this small cylindrical area is dA and length dx. Of course, so this length is dx. So each cylindrical area or each cylindrical element will be of length dx and area dA. Now that cylinder, elemental cylinder, is taken at a distance of y from the neutral axis. So this elemental area is taken at a distance of y from the neutral axis. So from here the distance is y. So now let us write it out so that we can remember later on. Okay, so then what is dA? dA is the area of elemental cylinder. Okay, video got paused. Let me check. Okay, this is now working. Okay, so here dA is the area of elemental cylinder. This is the elemental cylinder here. Dx is the length of the elemental cylinder. Y, small y, is the distance of elemental cylinder from neutral axis. Let sigma is the intensity of bending stress on the end of elemental cylinder on AB. Okay, sigma is intensity of bending stress or bending stress on the end of elemental cylinder on the section AB. Similarly, then in the other end, the stress will be sigma plus d sigma. Stress at section CD. So now the bending stress at distance y from neutral axis is given by the equation m by I equal to sigma by y. So from here we can get an expression of sigma is m by I into y. Now we will remember this equation. So bending stress on the end of elemental cylinder at AB, where the bending moment m, then the sigma can be written as this. So we can write at section AB, the bending moment working m, I is constant, and then we can find the expression of sigma, expression of sigma is m by I into y. So similarly, at section CD, at section CD, on the same formula, the stress will be, we have said, sigma plus d sigma, that can be written as m plus by I into y, because at section CD the stress we have written is this, and the bending moment is this. So now let us find out the forces on the two ends of the elemental cylinder. Okay, we have known the stress values. We have find out the stress values in two ends AB and CD. So force will be basically stress into area. So we can write the force on the end of elemental cylinder on the section AB. On the section AB, we can write stress into area. This is the expression of force at AB on this elementary cylinder. This is the elementary cylinder. This is the AB face and this is the CD face. So in the AB face, the stress value here is sigma and area is dA. So here the force working on this cylinder is sigma into dA. Now here it will be sigma plus d sigma into dA on the other end. So on the other end, before we discuss about the other end, let us put the values over here. In case of sigma, we have find out that it is m by I into y into dA. Now on the other end, force on the other end of elemental cylinder on the section CD. Then its value will be stress sigma plus d sigma, area is dA. Same, we put the value expression of sigma plus d sigma we have just found out in previous page, m plus dm by I into y into dA. Okay, now one end the force is this, other end the force is this, so they have variation. So now the net unbalanced force on the on the elemental cylinder, unbalanced force on the elemental cylinder. So one end is this, other end is this, so the difference between them will be the unbalanced force, m plus dm by I into y into dA minus m by I into y into dA. So from here we can get the value will be dm by I into y into dA. That is the unbalanced force on the cylinder. Now if we want to find out the total unbalanced force above the level EF, look at the picture again. If we want to find out the total unbalanced force above EF, so on this hatched section EFGH, then we have to integrate it. So the total unbalanced force the total unbalanced force above the level EF and between the two cross sections AB and CD and above the level EF. Can be found out the total unbalanced force above the level EF. Okay, this line has been written twice. EF and between the two cross section AB and CD, this line is written twice. The unbalanced force above the level EF and between the two cross sections AB and CD may be found out by considering all the elemental cylinders between the sections AB and CD above level EF. So what we are trying to say is, look at this image. We have found out the unbalanced force due to this one elemental cylinder. We are considering this area EFGH, which is above EF, between this AB section and CD section is made of a finite number of elemental cylinders. So if one elemental cylinder, for case of one elemental cylinder, if the force can be found out, the force can be found out for this total hatched area by integrating them. So integrating them, considering the whole area, the total unbalanced force is integration dm by I into y into dA. So dm by y integration y dA. So now if this dm by I is a constant, let it out. Integration of y dA means if the area of the section is A, then we can retain this y dA will be equal to A, means total area, into the distance of centroid of the area from the neutral axis. So here we can write this capital A is area of the section above EF equal to area of EFGH, and y bar is equal to the distance of CG of area A from neutral axis. So this is the total area of EFGH, and y bar is the distance of CG of EFGH from neutral axis. So now, due to this total unbalanced force acting on the part of the beam above level EF and between the section AB and CD, the beam may fail due to shear. So how does it will look like? Let me draw a figure so that you can understand how this will work. These are extended both ends. Okay, so this is the layer EF, and while the section is at a distance of dx, this is how this AB and CD, due to the shear, will come upon. So initially this was AB section is shifted, and this was CD section, but this upper portion is shifted, and shifted due to this force dm by I into A into y bar, and this is the neutral axis. So this is the way it will shift, and actually they will look like, the cross section will look like, this is your EF section, this is the CG of this EF GH section, this distance is y1, and this distance is y bar, actually this is y bar, and this width is b. Okay, so this is how these layers will be shifted and failure will occur. Hence, in order the above part may not fail by shear, the horizontal section of the beam at the level EF must offer a shear resistance. The material should offer a shear resistance against this shear force, and this shear resistance at least must be equal to the unbalanced force to avoid failure due to shear. So resistance should be at least equal to this, otherwise shear failure will occur. So now we can say that the shear resistance will be equal to the total unbalanced force to balance it for case of safety. Shear resistance has to be minimum value, has to be the total unbalanced force, otherwise there will be shear failure. So the total unbalanced force is dm by I into A into y bar. Now let us have the tau is the intensity of horizontal shear stress at level EF. Okay, so from this EF, this will try to slide like this way. So tau is the intensity of shear stress. Let B is the width of beam. Now for this length dx, the area on which the tau is acting, see tau is acting in this surface due to this length. This length is dx, this area, this width is b. So this area on which the tau is acting is this area of width b. So it will be b into dx. So the shear force due to tau will be equal to tau into b into dx. This is the area, this is the shear stress. So the shear force due to tau is tau into b into dx. Now this shear stress should be equal to the shear resistance. So we now equate the shear resistance value with this shear stress value. So tau into B into dx will be equal to the shear resistance, that already you have written here, dm by I into A into y bar. So from here we can get this tau is equal to dm by I into A into y bar by B into dx. Now we just change it, dm by dx into a y bar by I into B. Now this dm dx is actually the shear force. Dm dx is equal to shear force. If we divide the bending moment with length, what we get is force. So dm dx, here the shear stress is caused due to the bending stress. So this dm dx will be written as F. So F into A into y bar by I into B. So this is the expression through which we can get horizontal shear stress at the distance y1. Initially, what you have done, the shear stresses has been calculated on the vertical force on the vertical planes. If you can remember, while we have found out the problems on shear force bending moment diagram, we have taken only vertical stresses, only vertical forces, and due to vertical shear force we have drawn the diagram. But as we can see, due to this bending stress, the shear stress occurs also in horizontal plane, and that expression is given by this we have just derived. So but by the principle of complementary shear, the horizontal shear stress is accompanied by a vertical shear stress tau of same quantity. So sometimes this A into y bar is also expressed as the moment of inertia of area A about neutral axis. This A into y bar, this is also the moment of inertia. Sorry, this is not moment of inertia, this is a single time moment. So we can say this is the moment of area A about neutral axis. Moment of inertia is twice the moment to be taken. A y bar square is the moment of inertia, but this A into y bar is the moment of area, single moment. Okay, so this expression will be required for solving problems. Okay, we will quickly solve a problem. Just give me a moment to drink some water. Okay, wooden beam, 100 mm wide, 150 mm deep, simply supported over a span of 4 meters. If the shear force at a section of the beam is 4500 Newton, shear force F is 4500 Newton. It is asked to find the shear stress. Question is, find the shear stress at a distance of 25 mm above the neutral axis. Okay, so let us quickly draw the diagram. We will draw the cross section, that will be sufficient as length is given. Rectangular cross section. If nothing is given, you just go with rectangular cross section, no issues. And of course this will be rectangular as wide is given and deep is told. This is rectangular. So this is 100 mm wide, 150 mm deep is told on the problem. Okay. It says the shear stress at a distance of 25 mm above neutral axis. You just uh, give this at 25 mm from the neutral axis. So now you can hatch out the area, and this is 25, that means this is 75, 150 by 2, this is 75. So now this much is then 50 mm. So if this is 50, the CG will be here. The CG will be how much? This will be 25, this will be 25. So the Y bar will be actually 50. Okay, from the image we can understand Y bar will be 50. So now let us find out area is 100 into 50. The hatched area 100 mm width, and depth is 25, sorry, the depth is 50. This hatched area depth 50. So 100 into 50, we can write 5000 millimeter square. Okay, Y bar is the distance from CG of the area A from the neutral axis. So this is, we have already found out from the geometry, it will be 50 mm. Moment of inertia to be found out is BD cube by 12. Put the values, 100 into 150 cube by 12. So upon calculation we get 28125,000 millimeter to the power 4. B is already given 100. So now we have the formula just derived. Tau is equal to F into AY by I into B. This is the formula. You put the values over here. F is 4500 Newton given. Area is taken as 5000. Y bar is 50. I is, just put it here, 28125,000, and this breadth is 100. Okay, put the value. Finally we'll get 0.4 Newton per millimeter square. So shear stress at a level of 25 mm from neutral axis, the horizontal shear stress is 0.4 Newton per millimeter square. This is a very easy problem. Similarly, if we go for another problem, okay, here a beam of cross section of a isosceles triangle is subjected to a shear stress, subject to shear force of 30 kilonewton. Okay, triangular cross section, it is given, isosceles triangle. The shear force 30 kilonewton provided. Base width is 150 and height is 450. Base width is 150, height is 450. Now determine the horizontal shear stress at the neutral axis. Okay, neutral axis will be from the CG. Find the horizontal shear stress at the neutral axis. Let us write them out. Horizontal shear stress at neutral axis. Number 2, the distance from the top of the beam where the shear stress is maximum. Distance from the top of the beam where shear force is maximum. Number 3, the value of max shear stress. Okay, so base we name them